In BSC, each block is preceded by several 8-bit patterns called the synchronizing or SYN characters. Since I've picked IBM's BSC for this example, let's say that the SYN character, and in fact all the characters, are in IBCDIC code. That's an acronym for Extended Binary Coded Decimal Interchange Code, which IBM uses instead of ASCII in most synchronous systems. After the SYN characters comes the data block. This is where the mass transit aspects of synchronous become obvious. The message text is loaded into data blocks like commuters into rail cars and sent en masse. Each block of data consists of 2 or more SYN characters, a start of text character, the block of text itself, then either an end of block or an end of text character, and 2 block check characters. Finally, there may be 1 or more pad characters. Let's examine each of the components of the block in greater detail. Suppose this alpha string, "this is the text," is actually the text to be transmitted. A real text might be much longer, but this is all that'll fit on my felt board here. To begin, the transmitting device breaks the text up into blocks. I'll break this up into blocks of 3 characters each. Okay, a real system would put more characters into a block, but this is easier for me to handle. Now, at the beginning of the first block, I'll put a start of text character. That's logical. Similarly, there should be an end of text character after the last block. Now, after the first block, there should be something to say, "That's all the information in this block, but expect more text." And that's what this end of transmission block says. That says it to the receiving device. I'll put an ETB character after each of these blocks. Okay? Now, there should be some sort of special start of block character for each of these blocks, right? Wrong. Sorry, it just doesn't work this way. Every block is preceded by the start of text character. The first block, the last block, any block in the middle. It's all the same. So we'll put a start of text character in front of each block. Okay, what else do we need? Well, this is synchronous data transmission, right? Every block must have 2 synchronizing characters right at the beginning. There are 1 or more characters to be added to each block now. And 2 more. Okay. Now, as I said, there are 1 or more characters to be added to each block now, and they're the block check characters. And they're at the very end of each block. The block check characters permit the receiving device to determine if it has if it has received the block correctly. Remember the parity bit in asynchronous ASCII? Well, block check characters are like a super parity bit for IBCDIC. When the transmitting device sets up a block, it performs a calculation based on the number of 1s and 0s in the block. LRC for longitudinal redundancy check is a simple process. CRC for cyclic redundancy check is a bit more complex. But in either case, LRC or CRC, the result of the calculation is sent as block check character or characters. Now, at the other end of the line, the receiving device performs the same calculation on the block and compares its results to the block check character. If the 2 agree, fine. If not, the receiver asks for a repeat. You see, after each block is sent, the transmitting device waits for an acknowledgement. That is, it waits for a synchronizing character and the acknowledged characters. It must have that before it'll go on to the next block. If it gets the negative acknowledged character, it'll retransmit the last block. This goes on as long as it takes to get all the blocks transmitted correctly. You'll notice that this implies something about synchronous terminals. They must have a buffer to hold a text until it's sent completely and correctly. Not every block transmitted in a synchronous system contains data. Sometimes it's necessary to send heading information relative to message identification, priority, or even, as I'll explain in a few minutes, the address of the receiving device. When heading information is sent, it's preceded by a synchronizing character and the start of heading character. The actual heading information can be followed by either the end of transmission block character and a block check, or it may be followed by a start of text character and a text block. Now, there's still more to VSE that I won't go into in this program, primarily characters that are used for line turnaround. There's also transparent text mode, which allows control characters to be sent as part of the text without affecting transmission. You need to know that these capabilities exist, but I don't want to explain them in detail in this program. I do want to go into detail on the subject of polling. Remember I mentioned that heading information could include the address of the device to which the message was directed? That's very important. In the asynchronous systems we've talked about in other programs, every terminal required its own data line. Now, that might be fine for low-speed lines where charges are low, but the phone company charges a lot of money for really high-speed lines. So, to get your dollar's worth, you have to be able to use more than one terminal per line. Or, look at it another way. Remember the Tektronix order processing department? 10 clerks and 10 terminals in one area, all doing essentially the same job? It would be inefficient to supply a separate data line from the host to each terminal. Synchronous communication systems permit a cluster of terminals to share a data line. Naturally, all the terminals on a line can't be allowed to put data on the line haphazardly. There has to be some way of imposing order, some way to make sure that only one terminal at a time can use the line. The set of rules that allows this is called a polling protocol. Let's examine what happens at the two ends of the data transmission line. At the host, or mainframe, a port is defined by specifying the addresses for the terminals, data rates, command codes, and so forth. Port definition is a software process. The device that handles the data between the host and the modem on that end of the line may be called either a front-end controller or a transmission control unit, abbreviated TCU. Different sorts of TCUs may be required for different sorts of data entry and remote job entry terminals, or a general purpose TCU can provide individual ports for a variety of devices. On the other end of the line is another modem and a device called a remote controller. This controller then feeds a group of terminals connected as a cluster or a chain.